5, 6, 7, 8. Okay, today's lab is on conservation of energy and the work-energy theorem. So work and energy are two closely related quantities. Energy is a storage of, energy measures how much capacity to do work something has. So you can kind of think of energy and work a little bit like money in your bank and your paycheck. Okay? Work is a transfer of energy in and out in different forms. And just like your paycheck is a transfer of money from one place to another. So if we want to describe the energy of a system, if it's a closed system, meaning there's no opportunity for energy to leave, that means energy has to be conserved. And specifically, if we don't have friction or air resistance or any of what we call non-conservative forces, then all the mechanical energy is conserved. And whatever kinetic energy the system has, plus any potential energy it has, is constant. So whatever the initial kinetic plus potential energy is, you have the same amount of energy after some period of time. So the final kinetic energy plus the final potential energy equals the initial kinetic plus potential energy. So that's conservation of energy. We're going to test that today in a system where we measure the initial kinetic potential energy, and then we'll measure as a function of time how those quantities change, and we expect to see them at their sum conserved. Now, if we want to talk about work, work is the transfer of energy, in this case from potential to kinetic. We're going to have gravity doing work on a falling object. So the object has some potential energy. As it falls, gravity pulls on it, and it converts that potential energy into kinetic. Okay, so the work done, it's just the amount of energy that gets changed. And so the net work done in a system must equal how much its kinetic energy changes. That statement is called the work-energy theorem, and we're going to test that as well. So our system for testing these things will look like this. You see it on your tables. It's a cart on a track that's free to roll. There's a pulley in the form of our rotation sensor, with a string going over it attached to a falling mass. Okay, so when we set this up, if we put some mass here on the end of the string and let go, we expect it to fall down and to pull the cart over. And by weighing this mass, we will know the force pulling it down, and we will be able to see its potential energy get converted into kinetic energy. The rotation sensor will measure how fast the string is being pulled over, and that will tell us how fast these two objects are moving. We can use that to figure out how much kinetic energy they have. By figuring out how far the rotation sensor is rotated, we can also figure out how far these things have moved. It's going to tell us how far this has fallen and how much its potential energy has changed. So with this one sensor, we can determine both the potential and kinetic energy of our system. Okay, so let's look at some free body diagrams for the parts of our system. Let's look at the cart. What forces act on the cart? So there's a normal force. What else? Yeah, so there's weight, which weights down. There's tension in the string. And assuming this is a frictionless system, that's it. Okay, so it's pretty clear this is going to accelerate to the right when there's tension in the string. How about the falling mass? What forces act on it?
Gravity.
Okay.
Tension.
And tension. Okay, now assuming that this is a perfect pulley, then this tension is the same as that tension. And so we can look at this and we can ask, for our system, what is the net work done in the system? So work is force done with displacement. Okay, so as the system moves a certain distance, so as the pulley rotates through an angle delta theta, the distance that the objects will have moved is what? If the pulley has a radius of r. Can you figure that out? So, recall that an angle, theta, measured in radians, is defined as the arc length of an arc at a distance r relative to that distance r. Okay, so, as the pulley rotates through an angle theta, the distance the string moves is this arc length s. Okay? That's also the distance that our block falls and our part moves over. And so we can rearrange this and say that delta x is equal to r times delta theta. Okay, so let's write the work for all 5 of these forces. See if we can figure out what the net work on the system is. So this is the form for work. What is the work due to the weight of the cart?
Can you say it again?
What is the work due to this force here, mcg? Yeah, why is it 0? Yeah, the force is pointing down, but the displacement is to the right, so it doesn't do any work. So, same is true for the normal force. It doesn't do any work because it's pointing up, but the cart's going to move to the right. How about the work due to the tension on the cart? So, what's the force? Tension, T. What's the displacement? R delta theta. And are those, what's the angle between those two? They're parallel, right? So the dot product, remember, is the magnitude times the magnitude times the cosine of the angle. Right? That, for parallel, that cosine is 1. So this is the work done by tension. What about the work done by tension in the falling mass? Tension points up. Displacement is still r delta theta, but what's the angle between them? Yeah, so what is the work?
Sine?
What's cosine of 180 degrees? Yeah, so the work is negative. Right? When an object is pulled, when an object moves in a direction opposite to the force acting on it, that force is negative work. So that's what we see there. And then the work done by gravity on the falling object. What is that? Here's the force. The displacement is r delta theta, and what's the angle between them? 0. So is this positive, negative, or? Yeah, that's positive. Okay, so let's add all these up, and we'll get the net work. 0, 0, a positive and a negative quantity that are equal and opposite, so those cancel. And so the net work is just that due to gravity. Okay, so that's one of the things we're going to keep track of. The net work. about the kinetic energy? What is the kinetic energy of the system? That's one of the things that I want to keep track of over time. What's the formula for kinetic energy of a translating object?
1/2 mv squared.
Okay, 1/2 mv squared. So, now which mass? I have two masses in my system.
The following.
The falling mass? Anyone have a difference of opinion? I want to keep track of the total kinetic energy of the system. I have to keep track of everything that's moving. Is the falling mass the only thing moving? Yeah, both of them. So, because they're both moving at the same speed, they're connected by a rope, then they're both going to have the same velocity, so I can just group their masses together like this. And what is the velocity? I'm not going to be able to measure velocity directly. I'm going to measure angular velocity. So angular velocity, we've done this before. With the rotation sensor, angular velocity is the rate of change of the angle. Okay, so that means d theta is omega dt, and velocity is dx dt, and x is r d theta. So velocity is r times omega. So for velocity here, that r omega squared. Okay. Omega will be recorded by our data logger. Right? It will record the angle of the rotation sensor as a function of time, and it will also record the rate that the angle is changing as a function of time. It will call it velocity, but it's not. It's angular velocity. We need to multiply it by the radius of the pulley to get an actual linear velocity. And your lab manual reminds you to do that. If you forget to do that, your results will be off by a factor of 40. Okay, how about potential energy? What is the potential energy of my system of moving masses? What is the form of gravitational potential energy? What does it look like? MGH. So we're going to have something that looks like MGH. And again, we have to ask, which mass do we care about?
Isn't the falling?
Okay, we're going to care about the falling mass. Does that mean that the cart doesn't have any potential energy? Or do we just not care about it because it's not going to change? The cart's moving horizontally, so its potential energy isn't going to change. So whatever the cart's potential energy is initially, it will be the same thing afterwards. Only the falling mass is moving up and down. So that's the only one we actually need to keep track of. And for h, the height of the mass, it starts at a height h naught, and it's moved a distance r delta theta downward, then this is how high it is. And finally, we're going to want to know the total energy. So we'll add up the kinetic plus potential to get the total energy. Those are the four quantities we're going to want to keep track of in this experiment. Okay, so you can see that most of the information, delta, theta, and omega, come from your data logger. You'll need to measure the mass of your cart and your falling object using the scales that we have up front. And you'll need to measure the radius of the pulley that you're using on the rotation sensor. You've done this in a couple different labs already. So the vernier calipers are out. And you'll need to know the height that your mass starts from. It's going to turn out that this quantity actually doesn't matter, because I mentioned we only care about changes in potential energy, and that quantity is not changing. But just for clarity, you can go ahead and measure that using a meter stick. Okay, so you'll have all of these quantities measured, and because delta, theta, and omega are measured as a function of time, you'll be able to plot them as a function of time. Or you'll be able to plot them as a function of displacement, which is actually the way I want you to plot it. Right? If you do it as a function of displacement, your plot should look like this. So when you import these into the computer, it will generate some graphs for you. Those graphs are going to be some quantity versus time. You'll have to change both the quantity that's plotting on the vertical axis and the horizontal axis. I don't want it versus time. I want it versus displacement. Okay, so your graph should look something like this when you're done. We expect that the kinetic energy is increasing as the object falls. The work done on it increases. The potential energy decreases. And the sum of kinetic and potential energy should be flat. That's what we expect. Now, in order to say whether we've measured that or not, of course, we need to keep track of uncertainty. So we have these formulas. You can see they're all made up of sums and products. So you know the sum rule and the product rule for how uncertainties add. So if you estimate the uncertainty in each quantity, you can determine a formula for the uncertainty in each of these calculated values. Just like last week, include that formula as a calculated column in your spreadsheet, and then tell Logger Pro to draw error bars using that calculated column. You'll get something that looks like this. And at that point, you can quantitatively say whether or not you observed conservation of energy. So, for instance, if this total energy line is not perfectly flat, then you might be tempted to say, well, energy wasn't conserved. But if you have error bars on it, you can draw a flat line. And if your flat line goes through 68% of the error bars, then you can say that your observations were consistent with conservation of energy. Okay. If there's a significant trend such that you can't draw a flat line that goes through most of the error bars, you won't be able to say that. Likewise, we want to verify the work energy theorem. So we're going to look at our plot for the work and the kinetic energy. And we want those two lines to agree. So you can count the number of error bars that one of the lines goes through. Right, so the best fit line for the work, count the number of error bars in the kinetic energy curve that it goes through. If it goes through 68% or more, you can say that they agree. Any questions on the analysis? Okay, then just one comment on the experimental procedure. Your lab manual describes the method for doing this, but I thought I would mention it as well. All of this assumes that there's no friction. Okay, now there is friction in our system. So we have two ways of dealing with that. One is we can try to estimate how big it is and include that as an uncertainty. Or what we're going to do is we're going to try to compensate for it. So your cart has a little bit of friction rolling on the track. So what you're going to do is, it's got this adjustable foot on one end of the track. So by turning it, you can raise or lower the end of the track. You want to tilt the track up just enough that the tendency of the cart to roll downhill is going to overcome, or just about overcome, the friction trying to oppose its motion. Okay, so what that means is if you give it a little nudge, it'll roll at constant speed without stopping. Of course, it won't do that backwards, right? When you're going backwards, it's not only going uphill and it's overcoming friction. So your system won't be perfectly flat, it'll be slightly tilted. So make sure you set up your track as such so you can we can operate under this assumption. Okay, we can go ahead and get started.